All right, here we go, our first video lecture. Okay, we are going to talk a little bit about section 13.1. We'll get through most of it. We will probably also need to do a little bit in the next video as well. 13.2 is not quite as long of a section, so we should be able to do that fairly easily. So we're going to look at, what is a vector, what are some of our basic vector operations, and different ways that we can represent vectors. So we'll start with some definitions. So with vectors and scalars, vectors are quantities that have both a direction and a magnitude. And we do represent them with an arrow. They have a starting point and an ending point. We'll talk a little bit more in a couple of slides here about what that exactly means. Scalars are quantities with magnitude but no direction. So sort of the biggest example of the difference between scalars and vectors is that velocity is a magnitude, or it's not magnitude, it's a vector. Because when you're talking about velocity, you're talking about, yes, I'm going 10 feet per second, however long, and I'm traveling east. I've got a way that I'm going, I've got a direction that I'm moving in. When we're talking about speed, that's a scalar. A speed is just, how fast you're going. Speed doesn't take into account that we're maybe moving forward or moving backwards. And that's something you talk a lot about in 252, that's the difference between speed and velocity. Velocity is directional. It's telling you which way you're going. So another way to look at that is that it's a vector, that we've got the speed that we're traveling, and then we've got the direction we're also traveling in. So two vectors to be equal, they have to have the same direction and the same magnitude. So for example, if we grab this guy here and we copy it, and I guess I have to hit paste, there we go. Now this vector right there, those two are equal vectors. They are in the same direction and they have the exact same magnitude because I literally just made a copy of it. So that's the idea of it. We can take a copy, move it around, and it's the same exact vector. The zero vector, that's a little bit of a funny kind of thing. It has, let's make sure with the pencil here, it has length 0 and no direction. It's kind of boring. It's just basically a point. There's the zero vector. It doesn't go anywhere and it has no length. Okay, so there's a couple different ways that we can represent vectors. And so let's take a look at that. So we've got our arrow here, and I'll grab a different color here. Let's see, the start is the tail, the end is the tip, and then this distance that it travels, that is its magnitude. And that is just a fancy word for its length. So don't think that it's anything fancy. And that direction that it's going is from the tail to the tip. So that arrow is telling you the direction that it's going, and then we get that solid point for the tail. So we can also set these vectors up to be in the coordinate plane. And again, if we want to, we can have a bunch of equal vectors. I could grab this guy and I could copy it and I can paste it and I could put it over here. And then I could copy it. Oops, go put you back. Go back down there. We could copy it again. We could paste it again. And we could have a whole bunch of equal vectors sitting here in our coordinate plane. When we do have a vector in the coordinate plane, this is 2 dimensions. We're here in 2D. This is usually represented east and west on the x-axis and north and south on the y-axis. This vector right here sitting with its tail at the origin, this is also called a position vector. We've positioned it so it's starting at the origin and then going off. to some sort of point where it ends. And because it started at the origin, that point where it ends, we could label it on the x and y axis as AB. And so that point right there, AB, that can give us a way to talk about that vector that's sitting there with its tail at 0, 0. So we could name this vector if we wanted. Call it vector v. It's kind of our standard name for a vector is v, very original of us. So v, it is AB. This is one way that we can note this vector and talk about where it is. So all of these vectors that we have drawn here would be vector v, all of these here, because they're all equal. And we can talk about them in this sort of component form here, A, B. And let's see, some notations that you're going to see. I will always draw vectors with a little arrow on the top to note that it's a vector and not that it's a variable, so different. When you see them in textbooks, they'll be bolded. So another thing that we can do, and maybe we can do that here, is we can do scalar multiplication. So a scalar is just a numerical term, so it's a number. So I don't think a scalar is anything fancy. So if we did 2 times our vector, this would be literally 2 times a and 2 times v. And this would be twice as long as v. So let's get our arrow over that. So scalar multiplication is pretty straightforward. Let's look on here. I think we do have, a slide for this. So here's what I'm talking about here, that a lot of times we see vectors bolded in textbooks, but because it's hard for us to write that as bolded, we put a little arrow over it. So scalar multiple over vector, v, is c times v, and c times v, that length is the absolute value of c times v. So just like we had in the last slide, that when we had 2 times our vector v, we got a vector that was twice as long. So if c is positive, then c times v is in the same direction as v. If c is negative, then c times v is in the opposite direction as v. So it goes the opposite way. So if we had a vector, v right there, and then we did -1 times that, it would go the exact opposite direction. Let's take a look at some vector addition and subtraction. It's pretty straightforward, which is really nice. So let's grab a couple vectors here, some that we can make up. Maybe 4, 2, and then w can be 3, -1. So we could graph these vectors as position vectors. So here would be v, and again, a position vector, it starts at 0, 0, and then it ends at these x and y coordinates that were given here for a vector. So it's going to stop when x is 4 and y is 2. So it stops there at 4, 2. Our other vector, which I should have drawn in a different color, but that's all right. There's w. It's going to end right here at 3, -1. So if we wanted to find, let's grab maybe orange here, v plus w, this is as simple as adding our corresponding components. So we're going to get the vector 7, 1 when we add those two together. If we wanted, we could graph that. There's our added vector. Something you can notice about this is that if we take vector w here and we copy it and paste it on there, whoa, that took the whole thing. I just want to grab that a little bit, see if it can do it, see if my pen is smart enough to just duplicate that little guy. Not so much. Bummer. Okay, that's all right. We can draw it again. We'll draw it in blue here. Notice right there, that vector right there is vector W. It's parallel to vector W. It's got the same length. It's got the same direction. And similar to this, if we go this direction, this is parallel to vector V. That is vector V. Notice we make a little parallelogram when we add those two vectors. So let's see if I can easily, I think I can, erase these guys. Hooray! That we can do. Oh no, took out my orange vector. I'll put you back in here. There we go. Now if we wanted to subtract these, if we wanted to do the minus W, that again is literally as simple as subtracting the components. So we get positive 1 and positive 3 when we subtract them. And that goes up here like that. Now take a look at this vector right here. If we go from the end of V and go the opposite direction as W, so same length but opposite direction, we get to this vector right there. So very cool, kind of cool. Let's see if there's anything else I wanted to do on this slide. I think there was, just to show us that if we wanted to do that scalar multiple, so again, it's just multiplying each component by that scalar. So our scalar multiple of W, 3 times W, see, did I go all the way to 9? I did, hooray. Our scalar multiple would look like that. So that's 3 times RW. So same direction, but the magnitude now is 3 times as much. Okay, so magnitude, how we find that is, say we're given 2 points in the plane and they create a vector. So let's go, for example, point P would be at like 2, 1, and point Q would be at 4, negative 3. So P would be right there, Q, 1, 2, 3, 4, and negative 3. So our vector looks like that. Vector PQ. If we want to talk about what that vector is in component form, it's going to be that negative 3, oops, not negative 3, it's going to be 4. It's going to be 4 minus 2, our x value subtracted, and notice it's doing x2 minus x1. x2 is in Q, y1 is in P, and then we've got negative 3 minus 1, so we've got 2 and negative 4. So let's plot that point to negative 4. There is our position vector. So again, same vector, just scooched over. The magnitude of this, which is its length, and sometimes it's used with sort of single absolute values. Sometimes you see it with a double bar. It's the same. It's kind of different notations in different books. So we take those x values subtracted squared plus our y values subtracted squared, or we could have taken the position vector and squared each of our positions, because notice that's exactly what we're going to get. And we get the square root of 4 plus 16, which is the square root of 20. Do be careful when you're squaring your negative numbers. Okay, those should be positive. And square root of 20 is fine. I'm not like super picky that you have to write this as 5 or 2 square root of 5. I mean, I will later for something, but I don't get too picky about that if you don't do that. All right, unit vectors, we're getting close. It's kind of nice down here at the bottom, it tells us where we are. So unit vector is any vector of length 1. And so vectors of length 1 are really nice because their length is 1. We don't get weird answers like square root of 20. So we have 2 coordinate unit vectors. We call them I and J. I is the vector 1, 0. J is the vector 0, 1. So I is that little fun vector right there. and j is this little fun vector right there. I is going due east and j is going due north. We want to put that back in terms of position. Okay, so this gives us another way that we can represent our vectors. They can be multiples of these little coordinate vectors. So for example, we had our vector 4, 2. If we wrote that as 4 times that east vector, our 1, 0, and 2 times our north vector, which is 0, 1, we would get 4 times I plus 2 times j. So this is just another way that we sometimes write vectors. We write them in this 4i plus 2j format, and it means the same thing as if we write it like this. So I'll try to go back and forth between those two notations because they mean the same thing. It's just different ways that we can write it. So lastly, we've got an example here. We want to find two unit vectors that are parallel to our vector that we've been looking at here. So a parallel vector, vectors are parallel if they are scalar multiples of each other. So any scalar multiple, positive or negative, of v is parallel to v. So remember v is this guy right here. So right now, its magnitude is 4 squared plus 2 squared. So we end up with that darn square root of 20 again, or 2 square root of 5. If we want to shorten that up so that its magnitude, its length is 1, if we take 1 over the magnitude of that times our vector, this is going to be a unit vector. And this is okay because this guy is a scalar, so that's just a number. 1 over a magnitude, magnitude is a number, so 1 over that magnitude, it's still a number. So our magnitude was 2 square root of 5, and if we multiply that by our vector, 4, 2, we're going to get 2 over the square root of 5 and 1 over the square root of 5. You do not need to rationalize any denominators or anything like that. And our little unit vector, this guy here, it would be about, oh goodness, I did these, be about right there. This guy is approximately 0.89 and this guy is approximately 0.45. So this is one possible parallel unit vector. Another one would be just simply the opposite of our magnitude times our vector. Let me get my handwriting fixed. You've probably already seen this in class that I sometimes have terrible handwriting on my iPad. I wish it was better. But both of these two vectors, they are parallel to our original vector and they have magnitude 1. If you wanted to check that really quick, if we wanted to look at what the magnitude of this vector was, we could take its components and square them. Lost my square root there. And lost my square root on that one too. We get 4 fifths plus 1 fifth. So we get the square root of 5 fifths, which is 1. All right, that's the end of the first video here, and I will see you on the next one.